Good evening, everyone. So we'll start in 5 minutes.
Good evening.
आपकी क्लास है ना? एक्चुअली मेरी क्लास चल रही थी.
आज नहीं लास्ट में करते हैं लास्ट कर देते हैं नहीं है ना आज कर देते थे करते हैं एक बार ना आप जा तो
मैं बिल्कुल कर लूंगी, अभी मेरी चल रही है एक्चुअली। सर मेरी सर मेरे मैं आपकी बिल्कुल समझ रही हूँ, मेरी गवर्नमेंट के ऑफिशियल क्लासेस हैं, मैं अभी बीच में नहीं इंटरप्ट कर सकती, मुझे नहीं पता था मैं से। मैं आपकी बिल्कुल जाके बात खत्म करके करवा। हाँ ठीक है, मैं समझ गई। हाँ मैं समझ गई बिल्कुल। थैंक यू सो मच सर।
छह बजे के बाद हमें परमिशन नहीं है किसी भी क्लास में।
जैसे आपको ठीक लगेगा, मेरे को कोई प्रॉब्लम नहीं, बस एक बार
जैसे ऑल ऑफ है वो
मैं समझ गई। 8 o'clock, 8 बजे तक। Hi, give me just 2 more minutes, then we'll start. Okay. Hello, am I audible now?
Yes, ma'am.
Okay, okay. Thank you. Okay, sorry for this interruption. So let's start with this week 3 lectures. So first of all, a very good evening to one and all. And in this week 3 contents, we are going to study about linear classification specifically. Okay, so linear classification, which includes logistic regression, means logistic regression is one of the way in which you can classify your data. So how to use regression for classification purposes. Then another way for classification is linear discriminant analysis. We'll look into it. And lastly, there is a tutorial on Weka. You all have that. Okay, so most probably we will not get a chance to see how Weka, you can use Weka, but I'll try, because I have to include some more questions, as you have already given me a feedback that we can include some more questions, more mathematical concepts. So I'll let you to see the tutorials that is already available in your courses. Okay, so in your course the tutorial is given, and that tutorial is quite easy to understand. So I'm not going to give you an idea about how Veka means, we can't see it today. So let's start with linear classification. So in the last lectures, we have seen how regression works, how you have some supervised learning mechanism, some X, some Y, how to transform the X so that you can get an idea to predict Y, right? So in regression, you have seen the final output is a continuous number. But in classification, as you can see from this image, that it means it's a type of the output is in the type of some category or some ordinal value. Okay, so as you can see, the first thing is regression that you have already done. Second two things are classification. One type is binary, means yes or no. So it means if I ask you whether it will rain tomorrow, then it is called binary classification, because if you are saying yes, it means rain, no means no. Okay, so it means 1 and 0. But if you have multiple choices, it means what is the status of weather tomorrow, whether it will be sunny, it will be cloudy, it will be rainy. So these are multiple classifications. So basically we are going to study about linear classification methods. So linear classification, as the name suggests, it separates the data using a hyperplane. So what is hyperplane? Hyperplane can be considered as a single straight line, which you can see in the second figure. And otherwise, let's say you are sitting in a room, okay, and there are some objects flying in the air. Okay, so let's say there are two colored object, one is red, another is blue, and if you can put a cardboard in between those two objects, that is also called a hyperplane. Okay, so why the cardboard is considered as hyperplane? Because when you are in 2D, as you can see on this slide, that a single line can discriminate the two classes, but when you increase the number of dimensions, as you go in 3D or 4D or 5D, there we termed these discriminants or these planes as hyperplanes. Okay, so linear classification means a hyperplane will be there. And basically question arises, now how to do classification? So there are two major approaches to solve these type of problems. First is modeling a discriminant function. So as you can see from the second figure, it's a complete the line, the hyperplane is given to you, and you can easily classify that above the line there is a dog category, and below the line there is no dog category. Okay, or you can say the cat category. So it means how to model this discriminant function. So this line can be treated as a function which is used to discriminate the data. So that's why it is called discriminant function. So either you can use a function which can help you to discriminate the data, or the other thing is directly you can model this hyperplane. It means if I say just intuitive call, right, ki I have given you two types of data, you just have to classify them. So what you will do, you will just draw a boundary between them. So this drawing a boundary directly from a human mind perspective, I can say that is the second portion, that is directly modeling. So we'll see in maybe some upcoming weeks how to model it directly. Today we are going to see, okay, wait a minute. Hello. My voice is clear? Is my voice clear now?
Now
Yes,
it
ma'am.
is clear.
Ma'am, it's clear. I
Clear?
think crystal clear.
Okay, okay,
Yes.
okay, okay. Thank you. So, what I was saying to you that about linear classification, either you define or you model a function on the basis of which you can say, for example, let a function be fx. I'm talking in mathematical terms. The function is fx. If the final value is greater than fx, then you will say it is dog, or if its value is lower than fx, then we will say it is cat. So like this we will model a discriminant function, or we can directly model this. So we'll first focus on the first part. Okay. So what is a discriminant function? You can see from this figure, it's cluttered data, right? There are some red objects, some blue objects. And as you know from the regression perspective, um, is it my voice breaking? Is it like that?
Yes, ma'am. Little bit.
Okay. Okay, let me just reconnect then.
No, madam, it is clear only.
It's clear.
Hello.
Is it clear? I
Yeah,
mean,
I think that there
maybe.
is some technical issue for them, but
No.
I am receiving very clearly.
Okay. Then good. Okay, please check your connection. Sorry. All right. It breaks in between. Okay, let me just join it from other device. Maybe it will be helpful. Maybe. Let's say.
Continue after we see continuously 10 minutes, then we come to know that I think hopefully that is not your technical issue. Some other person, those who are joining,
I
the
think
signal
everyone
problem.
have the same technical issue.
Okay, now is it clear?
Everyone having the issue.
Ma'am,
It
can you
seems
please join from another device?
Yeah, now it is
Maybe
coming because of.
it helps.
Please, all of you close your microphone off.
Okay.
That is the resounding getting because of that.
All right. अगर if the voice break, please message me instead of using your microphone. Okay, so it can be helpful for everyone. Thank you. All right, shall we continue? Just thumbs up, yes, no. Okay. Yes. All right. So discriminant function. So we'll start with this. As you can see from the figure, there are some blue objects, there are some red objects, and there is a function which will associate with class 1 and class 2. So this function will help you to discriminate the final, the testing input, whether you will be classifying it as class 1 or class 2. So let us say the function is assigned to each class. So first thing that you will always consider that if there are n number of classes, so there will be n functions. Okay, so here there are two classes, so there will be two functions, and you can see from the figure the functions are defined using a symbol delta 1 and delta 2. So delta 1 and delta 2 are the two functions for class 1 and 2 respectively. Okay, next, the class with the highest function value determines classification. So it means what you want to do, let's say you will train your classifier and you will have n functions for n classes. Here there are two classes, red and blue. So there will be two functions, delta 1 and delta 2. Okay, so after getting these functions you can see, you can visualize them as we have done in the regression class. So we have already knowing how to uh, model the functions. So the modeling of the function is same as the regression purpose regression things which we have done in the last class. Okay, so our goal is to model this discriminant functions delta I means for the number of classes. So now after getting these two functions delta 1 and delta 2, if we have some input, we have some output for delta 1, we have some output for delta 2. Let us suppose there are two classes, blue and red. We have two functions, delta 1 and delta 2. Let's say I have a point to classify whether it should classify in delta 1 or delta 2. So what I will do, I'll pass the value in delta 1 and get the output. I'll pass that value in delta 2 and get the output. So obviously the maximum value given by the function will be associated as the class. If delta 1 is greater than delta 2, then obviously the testing element will belong to delta 1. It means class 1. If otherwise, it will belong to class 2. Okay, so basically we can say that this boundary which is shown to you in the black color can be said as where these two delta values are equal, that will be at the boundary case. So the boundary is where the value of delta 1 and delta 2 are equal. If it is greater for delta 1, then we say that the particular particle belongs to class 1, otherwise class 2. Okay, so this is called discriminant function. Now I think it is clear that what are discriminant functions. Question is how to model them, how to actually create them. Okay, so basically there are some conditions for linear separating surfaces. So we have already known from the regression perspectives that if we want to model any function that can have a form of y is equal to x beta plus epsilon. So you know here what is x here, what is beta here. So I'm not going to uh, uh, means go deeper into details. So you know what is y is the output, x is the input, beta is the model parameters. All right. So the approach for linear
Ma'am, once again delta 1 and delta 2 definition, ma'am.
Hello. Yes.
Delta 1 and delta 2 definition, ma'am.
Delta 1 and delta 2 are similar like you have seen in regression problems. Let's say you have only one class. Okay, so you model all the data. What you got from the regression output, like y is equal to beta 1 x1 plus beta 2 x2, remember?
Yeah, from the previous
Right?
class.
Yes. So now you will model it for each class. Right, so let's say you have three classes, so you will model the data which belong to class 1 will be modeled for with function 1. The data which belong to class 2 will be modeled for delta 2 similarly. Okay, got it. We'll have some questions related to that so that you can have a clear idea how to create them. Okay, we'll have a numerical problem with it also. So basically
Once times for the previous slide, once time graph slide.
okay, the graph slide, this one.
Yeah, ma'am.
Okay, so let's say you have this data and you want to you know regression, right? You still know regression, you don't know about classification. So what you will do, let's say I create an output variable in such a way that if I say that whether it belongs to class blue or not, it means 1 and 0. One question. Second question is it belongs to class red or not. So there are two things you want to model. First modeling is 1 and 0 for blue. Second modeling is 1 and 0 for red. So in this way you model two functions. It means there are two regression models, one for class blue, one for class red. So when you get two regression models, obviously the output will be 2. Am I correct? So if you have two regression models for the same data, it means you will get two outputs for both the models. Obviously. Now you have to say that which model is more appropriate for your data element. So the maximum the value of the function is will be giving you as the output or the class output. Okay, we'll see an example. So maybe you will get to know it more clearly. All right. Okay, so As I told you, there are two different approaches, either the discriminant approach or the hyperplane based approach. So we are going to discuss about discriminant approaches today. So first is linear regression, which you have already done. So we will see how linear regression can be helpful to classify the objects. It is because it's a strong mathematical model. What is the problem with that? So we can use the knowledge of linear regression and apply it for classification. Secondly, because it is not completely good approach, so next type of classification algorithm is logistic regression. There is some changes in regression, linear regression, and it changed to logistic. We'll see that. And last is LDA, that is linear discriminant analysis. It is more like PCR, like we have done in last class, principal component regression and the partial least square. Okay, so it's more related to that. So for regression purpose we use PCR and partial least square. For classification we use LDA or QDA, linear discriminant analysis or quadratic discriminant analysis. We'll see in today's class. Okay, so and hyperplane based approaches we'll see maybe in the next weeks or some weeks, where we will see some algorithms which will directly model your hyperplane. So problem setup is simple. We have classes and input representation. Like in regression we have x and y, here also we have x and y. So we have y in the form of g, so there I have called it as y. Here I am saying that the y can take place from 1 to k. It means that if there are k classes, let's say cat, dog, rat, horse, so these are the number of different classes. So the output variable can be of any this label type. So I am labeling it as 1 2 3 2k. Okay, first thing. Second thing, x, which you already know, is a p-dimensional vector which belongs from the space r of p. So basically x is same as you have seen in the regression perspective. Now question arises, let's say your classes, okay, let's say my class output is dog, my class output is cat. So obviously you will say ki this machine do not understand these terms. It doesn't matter to it. It can only calculate. So we have to convert or encode them. So one of the K encoding is used generally for this type of purposes. Okay, what you want to do? So each class label is represented at one hot vector. So remember the name, one hot vector or one hot encoding. For example, let's say there are three classes. So what I will do, for class 1, the output will be in the form of 1 0 0. Just look at it. There are three elements. These three elements represent three classes. Okay, ma'am, in this model, G is your output, not input. X is your input, G is your output. And actually G is not your output. If you know the notation from set theory, Y is your output which can take the value from G. G has a set of 1 2 3 4 till k. Got it? So it means your Y output can have value 1 or 2 or 3. It means it is having the value from G. So G is a set which has the number of classes which you have. Okay. So this Y set, because it is not a particular number, that's why we converted into one hot encoded vector. So what is one hot encoding vector? As the example is given to you, for k is equal to 3, there will be 3 elements. So if the class is associated as 1, then first element is 1, other is 0. As for class 2, the second element will be 1 and others will be 0. Similarly, for class 3, the last element will be 1 and other will be 0. So, concludingly, I can say these three elements are which denotes as position, right? The column number is denoted as the class variable. So, if the 1 is present in first column, then it means the class 1. If 1 is present in the second column, then it is class 2 variable. And if 1 is present in ith column, it means that is of class I. Is that clear? So these are the basic representation that we will use today. Yahan tak, if there is any problem, then please go ahead.
No, ma'am, no problem.
Okay, right, good. Now, you know about linear regression, all right? So linear regression, how it is calculated, you all know about this. This is a simple function where you calculate beta, you know y, you know x, right? Now,
For classification, you just do one thing, because you have now you will be having linear regression for each class. So let us say there are 3 classes, so you will have 3 functions. So obviously your output will be a single value. So how you will take that? You pass your parameters, you pass your input to all 3 functions which you have modeled, and take the maximum value. That's why it is written here argmax over k. Argmax means the function which give you the maximum value, its kth, it means which function gives you the maximum value will be denoted the class k. For example, we'll see a problem maybe. Okay, so this is your simple last actually this slide is copied from the last linear regression, so that you can have an idea again that this is the function that we have to model. Remember this beta x transpose x inverse then x transpose y. Similarly, we will do here also. But how we will do, let's see. So this is your now problem. Okay, this is your question. So what I have done is I have taken the similar type data which we have taken in the linear regression problem, but now the y variable you can see 1, 2, 3. It means 1 means class 1, 2 means class 2, 3 means class 3. Now look, you can treat 1, 2, 3 as separate numbers and apply linear regression. Okay, not a problem. But still, you are not using the particular mechanism to denote it to the class, because linear regression output is in continuous form. So you will have maybe 1.1, maybe 3.3, maybe 5.5, maybe 6.7. You will have those outputs also. That's why we have to somehow mold the information that we have learned in regression perspective to this classification ones. Okay. So for first thing, what we have to do, we have to encode y. So you can see here one hot encoded y, in which I have just used 100, 010 or 001. If we have 4 classes, then 10 is appended at the end also. Okay. So this is your x1, x2, y. Now what we will do is we will just apply linear regression, simple linear regression. You don't have to do anything. Just now y is changed. Y is not a single column attribute. Y is now 3 column attribute. So the matrix of y, the dimension of y increases. And how many dimension? According to the number of classes. If you have k classes, you will have k columns in your y matrix. This is the simple change. That's it. Okay, so I am going to the first step. What we have done in the regression portion, we define x, capital X and y. So what we have done in the x, can anyone tell me how we defined x in the linear regression? What we have done?
We have taken the x values.
Yes, and what something we have actually appended there?
1 in the first column.
Correct, very good. So what we will do? We will do the same thing. We'll append 1, we'll take x1 and x2. So now there are 9 inputs, okay, 9 rows, and there are 3 columns. 1 is appended. And now y is also used with one hot encoding. There y is a single column. Here y is 3 column. Is that clear? Is that good till now? Can we go ahead? If there is any issue, any problem at this stage, please ask. One hot
Yes,
y,
ma'am.
can
Clear,
I
ma'am.
have one? Yes,
Clear.
yes, yes. Yes, Ajit. One hot y, one hot encoding means only one at one place. Rest other are zero. That's why it is called one hot. Only one. Okay. Next we have to calculate x transpose. Can you explain the y here? Okay. Look, the y is your like this, right? Class 1, class 2, class 3. This is not 1, 2, 3. This is C1, C2, C3. It can be cat, dog, rat, right? So what I have done, I have encoded it. So basically you have, I think, learnt encoding in networking or something, where you just transform the data into mathematical form, right? So these categories are encoded in form of this mathematical form, where the position of the column in which the 1 is there denotes the class. If the first column has 1, it means class 1. If second column has 1, then it means class 2. If I column has 1, then it means class I. Okay? Is that clear? Who has asked the question about why? any sugar? Okay. Next thing. This is your next slide. It's a simple thing. It's simple. Okay. We use the one hot encoded y. So it means first column is representing your class 1. You just look, observe here. Let's say you don't have the other two columns, only first column is there. So what do you mean? It's a binary type of classifier. It means first three attributes are from class 1, last rows are not from class 1, right? Similarly, if you see the second okay, um, look, this 9 cross 3 is, it means the second column and third column in X is same as X1 and X2. We just append 1 in the left for the bias calculation. We have learned this in the regression portion. Okay, clear? Shall we go ahead?
Explain the matrix for y 9 cross 3.
Oh, this is the same matrix. Look here. This one hot encoded by 100. So these are 3 columns and there are 9 values. So these are used for the output. Can you see 100, 10? Yes.
Yes, ma'am.
Clear?
Yes, ma'am. Clear.
Okay. Okay. So now this is your X, this is your Y. You don't have to do anything. Just use your regression equations. So in regression equation, what you have done? X transpose X inverse. Okay. So X transpose X inverse, you can easily calculate. So ultimately what you have to do? This is your X. This is your X transpose. What you have to do? Multiply both these terms. So if you multiply X transpose X, you will get 3 cross 3 matrix. Okay. So this is your simple multiplication, matrix multiplication, simple. You can do that. Okay. Now you have to calculate inverse. So simply you can calculate inverse as like this. So this is your X transpose X inverse, simple as of the regression portion. No change, same. Now second step is, means third step is X transpose Y. So now Y has 3 columns. So it means some changes will happen here. All right. So next step is X transpose Y calculation. So this is X transpose, this is Y. You have now, in the last example, if this is a simple regression problem, then we will be having Y as 9 cross 1. But here we are having 9 cross 3, means 9 cross number of classes. So simply this is your B. All right.
Ma'am, why you are taking only 3 columns in Y?
Because there are only 3 classes in the data. In the
True.
data,
100. Okay, ma'am. Okay, ma'am. Got it.
all right, got it. So this is A, this
Yes.
is A and B are calculated. We just have to final calculate this equation. So this was your A inverse, this was your B. You have calculated in the last steps. You just calculate beta. Look here, you have beta in 3 columns.
How
There
did
you
we
have beta in single column. Yes, how? What's
how
your
did we get B as 3 cross 3?
just look out here. X transpose Y. X is 3 cross 9. Y is 9 cross 3. So you will get 3 cross 3 matrix. Correct? Matrix multiplication. Simple.
Okay.
All right. So now from this, you will get beta is like this. So now think of it. If there is only single column, we get one equation. That is beta naught, then beta 1 plus beta 1 x1 plus beta 2 x2. We have now 3 equation for 3 classes. First column denote first class, second column denote second class, third column denote third class. So just see y1, y2, y3. So there are 3 functions for your each class. So that's why it is written in the first line. The discriminant functions are created for each class. So these are the simple functions. Is that clear? It's a simple regression task, just that you convert your y into number of classes. That's it. Is that clear till now?
Yes.
Okay, now I'll give you a visualization how you will see. You have y1, y2, y3. Okay, so this is your training, all because this y1, y2, y3 is calculated from data. All right, that is already given to you. So this is your training part. Let's say this is your this graph. You can see this. Can you see this graph? So there are 3 classes I have made from the same data. So it's a blue class, pink class and yellow class. These are the three classes, okay? And this timer like symbol I have created here because I want to check whether this point belong to which class. So the point is 5, 3. So can you just intuitively from the human mind, can you tell me that which class does this particular point belong to?
Pink class.
Pink
Right?
class.
Okay, pink means there it is written as class 2. Okay, class 1, class 2, class 3. Just think about it. I have labelized it 1, 2, 3. Okay, because I have used y1, y2, y3, right? That's why. Now, how we will check that? So we have this f5 and 3. And obviously, when used with x, we append 1 with it, right? So we append 1 in that. 1, 5, 3. This is your simple x which you have to test. And what you have? Beta. So how the y is calculated? X beta. Just multiply it. You will get this. Just think of it. X is having a dimension with 1 row, 3 column, 1 cross 3 and 3 cross 3. You will get output 1 cross 3. So y dash is this, the last matrix that is given to you. Which is the maximum value you got here? You got 3 values, right? Which is the maximum one?
0.70.
Right? 0.707. It means from y2. First is y1, second is y2, third is y3. So y2 means the point will belong to class 2. And you can see here the class 2 is pink. Is that clear? So this is how regression can be used to solve these questions. It's an easy thing. Yes or no? You all have done regression in the last class. Correct? It's simple thing. It means we are applying. Just observe one thing here. In machine learning, because it is highly applicable in different domains, look how a simple how a simple regression problem can be transferred the knowledge to classification. But obviously, because these type of algorithms are not for ordinal variables, so there will be some disadvantages. Some cases will be there where these are not applicable. So I'll let you show one case. So the pitfalls, okay? So the same
Ma'am,
thing
in
has
previous slide, ma'am, how you get y1, ma'am? 0.06 0.7.
this x is multiplied by beta. How you
Okay,
calculate
okay.
y, right? Y
After
cap
that,
is
add.
calculated x beta.
Okay. And
Okay.
then add them by column wise.
Actually, it's a matrix multiplication. 153. 1 into
Yes, ma'am.
107 plus 5 into this plus
Okay,
it's
okay.
simple matrix multiplication. Okay. All right. So, what are the pitfalls? I'm giving you one example. Okay. So, the same example is there. There are 3 classes, but now I am giving you just single data. Okay. There are no 2-dimensional data. It's a single line. It means on the x-axis, some points are from class 1, some points are from class 2, and some points are class 3. Okay. Same linear regression, you know, ma'am, we can solve this classification problem. What's the problem? Let's do linear regression here. So what you will do, look, this I have given you a visualization. Same thing, some blue, pink and yellow. So class 1, class 2, class 3. Okay. I am doing same approach of linear regression here. Just see what happens. First is x and y. So what you will do, x append with 1. Y, 1 hot encoded. Clear? Just give me a thumbs up because I'm just repeating the step. So it means you are
Yes,
good to
ma'am.
go with
Clear,
the
ma'am.
next. Okay. Okay. Next thing, you just go with this A inverse, right? X transpose X. So this is your X transpose, calculate A and A inverse. Simple. Last step, same. Just that now X dimension is just less than the previous one. We have X1, X2 there. Here I have just X. Next step, X transpose Y. No problem. Calculate X transpose Y, simply B. Next is just final beta calculation, right? So just calculate beta as the same thing. We have y1, y2, y3, same. Just the difference is we have 3 terms there. Here we have 2 terms. Okay. So no x2 is there. Now I'll give you again a testing function. All right. So let's say I have to check for 0.6. Just look at here. So what I have done here, just see from this graph, there are these blue pink and yellow classes, which is already given to you. Okay. Now you will say, what are these lines? Can anyone tell me what are these lines? If someone has understood. What are these possible lines? How I have drawn them? Can someone just guess or say?
Using those equations
Y1
on a
coordinate.
previous slide.
Y1, Y2, Y3
Ma'am,
coordinate.
this line try to follow the pattern linear regression, something like that.
Yes, what you have said is correct, that the last equations, right? This equation y1, y2, y3 is like y is equal to mx plus c. It's a simple line, right? And you can plot the line with some points of given x1. So randomly I have taken some points and I just plot this line as y1, y2, y3. So I have choose the same color. For the y1 I have choose blue, for y2 I have choose pink, and y3 I have choose yellow. Now just look at this graph and let me know the 0.6 which class it should classify.
Class 2 में pink color.
Anyone else other answer if someone wants
Class
to
2.
give? Class 2. Class 2 के अलावा anyone say कि O is belong to class 1 or 3? Anyone?
Class 1.
Class 1. Okay. Point
One
number
point.
6. Just remember I am talking about x is equal to 6.
All
Okay.
classes.
All oh, it's not possible all classes. No, it should be
Second class.
so
No,
I'm
it is
asking you,
1 and 3, madam. Class 1 and 3.
I am asking you from the human perspective that what 0.6 should belong to.
0.6 is the pink color point, no?
Okay, right,
It-
correct.
Class
If I
2.
let you,
Class 2.
very good. Human intuition is class 2, and I also give you one hint here. In the data itself, the 6 is classified. Data is, look, just see the data. Just see, the 6 is classified as 2. It is given in the data. Okay. Now, after getting this only, what will I have? Let's see. So this was your simple 1 6. Same thing will do that, x into beta. Beta is this, and now look. So these from this and the thing that we have learnt just now, that the maximum of this y cap is to be taken. So the maximum value is 1.764 and it should belong to class 1, but it is not correct. So this is a very a very niche example in which you can say that not everywhere the regression can be applied for classification. All right. And in your terminology from the course, this term, they termed it as masking. So it means that actually when you will take any of the point, whether it will be classified into class 1 or class 3, it will never get classified in class 2. So it means this linear regression is actually masking your class 2, and this is not good. So it means there are some problem with linear regression which leads to another type of regression that is called logistic regression. So is that clear to you? So this is the first portion, that linear regression to classification is ended. Is that clear?
Can you repeat, please?
Okay.
Can you repeat?
So can you just look at this? I have the same example solved as we have done with linear regression for classification just now. I have another example. Here we can see that for the 0.6, from the linear regression, we classified it as class 1, but it should not be classified in class 1. Okay. Generalizingly, if you see the graph here, so either you will be classifying it in class 1 or class 3. You will never get classifying any number in class 2. Just take an example. Do it as a homework. You will never get it. So it means it is masking class 2. It means it is not. Why does masking work? You can say that ki, somehow this linear regression has a property for binary classes. For multiple classes, it is not able to get a clear boundary. So if and else condition type things, it will either be on the plane on this side or on this side. So because this class is somehow in between, so it don't have these type of linear boundaries. It should be having the straight lines actually. If I
Ma'am,
get this data.
suppose the boundaries were three vertical lines, no, will it not classify correctly?
But are you getting those vertical lines from linear regression?
No, no.
That's what the problem with linear regression. So we have to move towards another classifiers. All right. So
So,
that's
ma'am,
why
here, so ma'am, here we cannot able to determine in which class 6 is lie according to it.
means look, if you will create a classifier and you will give 0.6, it will give you something. I'm not saying it will not provide you the answer, it will provide you, but the performance, obviously as a human you can say that oh, the classifier is not correct. Let's say anyone, you give this task to some software developer and say make me a classifier, and it give you a demo and you say okay, this 0.6 should be in class think, but your model is not giving me in class 2. It means your model has
So
some
ma'am, here we
problems.
cannot able to determine properly exact class for 0.6.
Yes, you can say that. Yes,
Ma'am, does
that,
this
yes.
problem occur only if there are like multiple classes? Will linear regression work if there are only two classes all the time?
No, it's not like that, but because the term is linear, right? So you will either get some planes which are linear, which will not a good representation for multiple classes. So generally, we got this problem for high dimensional data, right? Okay.
But ma'am, this graph is also so that this data is not sufficient for linear because our scatter plot is horizontal, ma'am.
You can either state it in the other way. Either linear regression is not for this data or this data is not for linear regression. It means there is something that you need for a good classifier. Linear regression is not enough. That's what I'm saying. It's not like that linear regression will not help you, but it's
So
not
linear
enough.
regression is not properly fit here. This is
Yes,
right.
you can say that. Yes.
And basically, for the multiple classes, we are not means it is not recommended to use linear regression.
Yes, you can say that also. For multiple classes, we go for some other, means we have a line of approaches. This is just a beginning, right? So there are
Can we,
multiple. Yes.
is it like a linear regression will always work for two classes and it will never work for multiple classes?
Ma'am, we can't claim never like situation, okay? Sometimes maybe your data is so much clean in three classes like that, and your boundaries are completely separable. It means, let us say, you have three clusters, okay, in three directions. So maybe the linear classifier can be a good option, right? So I'm not saying ki it's every time for every data you will it hampers in many cases, because as you apply this machine learning in more complex environment, then obviously the boundaries of these hyperplanes often be complex also. So that's why this is a very clean data, this is also a clean data, you will not get this type of data. So in this way we can say that we need some more approaches for classification, so we are developing more approaches, so we have another way to see classification, right? Is that clear?
Yes,
We'll move
yes.
ahead. Okay, so next is logistic regression. So see this curve, okay? So you can see from the straight line it goes into some molds. All right, so this mold, this type of curve, you can say this is a function called sigmoid, as there are cubic function, as there are square function, as there are identity function. So this function is called as sigmoid, and we will now see how to derivate this function, means how to derive this function, why this function is important for logistic regression. So basically logistic regression, it is termed as regression, but it is a classification algorithm. Secondly, it models the probability of an outcome. Now, question arises that in a class type environment, it means if the final output is in the form of classes, why don't we talk about probabilities? Let us say you already see a cat and a dog, right? So there are different features of cat and there are different features of dog. Maybe they belong to a same color. Maybe they have tail, they have 4 legs. Most probably, if they are in a small age, so their structure is quite similar, but still you can classify them as a dog and a cat. And let alone you, let's ask a toddler, okay, who don't know much things. So how you classify it? You say, oh, if you are confused also, you say, I think it's a more probability that this is a dog because of some features, maybe some because of the structure of ears, maybe some because structure because of the tail, okay, some nose structure. So you can associate some probability of an outcome. So this probability things comes into picture, and now this linear regression turns to logistic one. So why this is called logistic? Basically, we start logistic regression to see the classification problems in terms of probability. So basic task is to convert all this thing what we have done in linear regression into probabilistic terms, right? Secondly, so because it's a very niche algorithm for classification, it is generally used for binary problems. So you have seen also, right? We have 3 columns for 3 classes. First column means one where class 1 is 1, otherwise 0. So it's more like a yes or no for class 1. Second column is yes or no for class 2. Third column is yes or no for class 3. So similarly, this logistic regression is used, it means it transforms the linear somehow regression problems to a classification problem, but uses a concept of probability. Now question arises, ma'am, why don't we have used the simple linear regression for probability? Because the output is not restricted, right? The output can be greater than 1, less than 0. You have seen that, right? And the probability has a strict restriction that the output should be restricted in between 0 to 1. Obviously, it's a probability approach. The probability lies between 0 to 1. So that's why, just see here, the infinite straight line just curved itself, transform itself using logistic regression between the values 0 and 1. So what we are saying, 0 means, that's why it is written as binary problem. 1 means yes, 0 means no. Okay, so that's how logistic regression works. Generally, it is used for binary classes. Next, we can apply it for k number of classes because of the knowledge transfer. Okay. So we'll see how to derivate this and how to get this, in fact. So logistic regression, now probability question comes into picture. Just look at the symbols that I am going to use, because this probability theory is going to be discussed in the whole class. So I'm going to solve one question also. So basically, just look at it. What we wanted output y, right? What is given to you? The input is given to you. So what I wanted, if I give you a picture, you have to tell me whether it belongs to class 1 or 0. So that's why it is written as, we aim to model probability of y is equal to 1, because I am talking about binary classification only. So I don't want 0, I want the probability of 1. If I know the probability of 1, then obviously what is the probability of 0? Can anyone tell me? Let's say the probability of y is equal to 1 is known, then how you can calculate probability of y is equal to 0?
And probability 1 minus probability of known thing equal to probability of non-known.
Probability of 0 is equal to 1 minus, correct, probability of 1. If the
1,
probability
yes,
of
ma'am.
1 is 0.9, then probability of 0 is 0.1,
0.1.
Yes.
right? Because the sum of probability is 1, correct? So that's why I always write here as y is equal to 1 means I wanted to calculate in 1, okay? Now, I can't calculate the probability directly. So I need some transformation. So what transformation I have used? The logit function. This is called logit function. Logit means it has log, and this, the other thing that is in the bracket, just look at it. The numerator is p of x and the denominator is 1 minus p of x. So you can associate like p of x is success, 1 minus p of x is failure. So log of success divided by failure is equal to your linear regression. I am just saying that. So what I am saying, what you are doing with linear regression, the output is not a probability function. Obviously, let's say, would not be it better that the three output that you got, and I say that took the maximum one, but it is very vague to say कि we get three values, we take the maximum one. Okay, intuitively it got it कि okay, the maximum one should be chosen, but would not it be good enough कि if I say these three values are like probabilities, so the most probable class is to be chosen. So now it makes some sense. Okay, so making this sense, I want the output to be restricted in probability domain. So probability means 0 to 1. So for that, what I have done nothing. I just choose the probability concept and I say this probability concept should be equal to the linear regression concept. I am just saying this. So what you have learned in linear regression, we are just transforming towards probability. So I don't know what probability function should I use, whether I should use any function that is already present, Gaussian, exponential, or which function should I use? I don't know. So for calculation of this function, I use this type of scenario that I wanted my success to be more. That's why success in the numerator and failure in the denominator. And I take the log of it because this log function transform it between 0 to 1 basically. And sorry, this probability is between 0 to 1 and log can lead it to more range, and it is equated to beta naught plus beta x. So you can either write beta x also because you have transformed x with 1 appended to the left hand side. That's why you can leave beta naught and use only beta x also, as which way you find it suitable for you. Okay, so this function is to be solved. Is that clear? So this is your logistic regression and I want to calculate this probability. मुझे नहीं पता ये probability क्या है. So I want to calculate it. So can someone calculate for me what is px? Can you solve this equation? How many of you just solve this equation to get the value of px? It's a simple one line equation, one variable equation where I want to find px in terms of beta and beta naught. No worries. I want to find what is px. How many of you can solve it? Just give your thumbs up or raise your hand. How many of you? Good, good, good.
Ma'am, suppose our data set is become more complex, yeah, more big. So then we can increase our RHS B0 plus B1 X1 plus B2 X2, something like that. Or this is
So this
restricted up.
b1 x1 is, this x is not a single term, this is a vector. So this beta include those beta 1, beta 2, beta 3. Beta naught is separately written. That's why I say you that you can in fact remove beta naught also. You can consider only beta x. So let us just have some mathematical portion here. Wait a minute. Okay, where I am here. So for logistic regression, your equation is log of px over this log of px 1 minus, it is going in insert mode. Beta x. Wait a minute. Now solve this. I don't know what is happening. Just solve it from your side and just give me the equation.
e to the power beta naught plus beta 1 into x upon 1 plus e to the power beta naught plus beta 1 into x.
Okay, correct. So how many of you got it? Let me know. Just raise your hand who have solved that. Others, please solve this equation, okay?
In week 3 assignment, this question is also there in the assignment.
I think I'm not able to.
The question is same question is there in assignment week 3.
Okay. So basically, let me just. So basically, what you will get is obviously what you have calculated is correct, and it is in the form of when you will divide your in numerator you got a exponential of beta naught plus beta x divided by 1 plus beta naught plus beta x. If you divide it by e to the power beta naught plus beta x, you will get this equation. So it is more simplified one. Okay. So what you have calculated is good enough. It's correct. The equation is e to the power beta x divided by 1 plus e to the power beta x. But if you divide and multiply this fraction with e to the power beta x, you will get this one. So beta naught plus beta x can be treated as beta x only. Is that clear? I don't know why I am not
So,
able
ma'am,
to.
solution of the above equation is the second line equation, Ax.
Hmm? What?
Second line is the expansion of the first line or solution of the first line.
Solution of the first line. Okay, I have to calculate p of x. So what I will do, I will take log to the right hand side. So taking log to the right hand
Yes,
side, it will
ma'am.
take exponential, right?
Exponent. Yes, ma'am.
So you just rearrange the equation. Px can be treated as one variable, and you will get this equation at the end. All right.
Is
So,
this called
ma'am, so
likelihood?
we need.
Sorry.
Is this the likelihood function or something?
No, this is not likelihood. This is the sigmoid function. This is the
Ma'am, we
sigmoid
can.
function.
So, ma'am, here we try to find the value of Ax.
Px, not ax.
Px. Okay, ma'am.
Px.
Because for only x we can also do differentiation, so constant term get 0 in one line.
No, I don't want x. I want probability of x. What is the
Okay,
probability
ma'am.
of x? So
Okay, ma'am, got
x
it.
is calculated from this function, and this equation is called sigmoid. That's why the before I have given you that GIF, right, in which your the graph is somehow molded in a S like function, that is called. Can explain please? So uh, did you get it, this first equation, who have asked this question? Okay, first equation, just solve it. Take log to the right hand side. Taking log here, you convert it into exponent, like plus is output is between 0. Yes, output is between 0 and 1. So probability hai na, this is probability, and probability is always between 0 and 1. So the output means the probability is always between 0 and 1.
So,
All
ma'am,
right.
we left logistic regression, linear regression, because probabilities lie between 0 and 1.
Yes. And I want the output in the form of probability, right? So I wanted a function, probability function. So for that probability function, I use the linear regression model itself and just equate it. So now this is called the probability. So if you have x, and if you have you have a linear regression, you know beta, beta naught, beta, you can calculate the probability of x also. Like you have in the last example, we have three values for one input. Okay, so for the sixth, what you have seen here, the output, the
Class 1,
input
class 2,
6.
class.
Yes, you have three values and you take the maximum. Now I wanted I don't take the maximum of that. First I calculate the probability and then take the maximum. I can do that. So now that simple thing is calculated in terms of probability now. I am converting those simple values into probability. So that's why
X is 9 by 2, no? Here. And that's if we take the same example as before, X will be 9 by 2.
uh, yes, just think of it X, you know, just think of it as single input. I'm not talking about bunch of inputs. I'm saying
Okay.
just calculate the linear regression and pass the x. The x is, let's say, 6. For x is equal to 6, you want to classify it, right? And you get 3 values. But those 3 values are not giving you the good results because these are not probability. So just pass those 3 values here for x, right? Because beta are different for y1, y2 and y3. So you will get probability of x when given y is equal to 1, y1, probability of x for y2, probability of x for y3. Now you can say this is the probability if the class is y is equal to 1. So this probability will give you more information. Okay,
But in
got
the
it?
case where X is X1, X2 like that, if it has multiple dimensions, how do we do this?
Just think of it, this is a linear equation. So there will be beta 1, beta 2. So how you will calculate beta 1 into x1, beta 2 into x2, beta 3 into x3?
So, ma'am, this equation is only valid for linear equation,
This
sigmoid
is linear.
function.
This is linear, you know. The thing that is written over there, beta x. Okay, you are saying. Let's say I have like. Are you asking? Like we have 9 inputs in the last example. Are you asking for that thing?
Yes, okay.
Let's say you have 9 inputs, na. So you will have 9 outputs also,
Yes, ma'am.
right? So the one first is associated, first value is associated with output input 1. There are different inputs. I'm not talking about inputs can be multiple. So you will have the probability for each and every x. Are you getting my point?
Ma'am, I am asking that this equation, logarithmic equation, log px by 1 minus px, this is for only linear equation or polynomial or something like that?
What, come again?
Ma'am, the equation you have written in, let's say, previous slide, px is, ma'am, px log px
Okay.
1 minus px equal to beta naught plus beta. So this is only for linear equation or polynomial or quadratic equation also.
Right? Just think of it. This is your linear regression output.
Yes, ma'am.
What you have in the last example, what you have seen here, कि the for x is equal to 6, you have 3 values, 1, 2 and 3. You say this is the maximum, right? This is a single value, right? In the previous example we have x1, x2, then y. Still in this matrix you have single value in which you have taken the maximum out of it. So the value is single, right? So whether it is
Okay,
x
ma'am.
square, whether it is
Okay,
x
ma'am.
cube, it doesn't matter. Here there
Okay,
will be
ma'am.
a
I got
single
it, ma'am.
value. Got
Got
it?
it.
Okay. So this is like the equation for your logistic regression. Now this function ensure probabilities remain 0 and 1. Now someone has given through a term of maximum likelihood. Still we are in linear regression because after linear regression we are calculating this beta and beta. But I'm saying that linear regression is not good enough. So how to choose beta? In linear regression, we use some matrix inverse. We calculate the beta using X transpose, X inverse and those things. Here what we will do. So here what we will say, this is for multiple classes. You can say we can skip it by this. So maximum likelihood means now we are talking about probabilities and just think of it. You are creating a model. So that model is to be like the probability of data should be maximum if you are creating a good model. So sigma 2
From the
sigma 3,
previous equation,
yes,
how did we come here?
uh, I'm coming to that.
Ma'am,
I'm
I
coming
have
to
I
that.
have a doubt from previous slide, ma'am. Ma'am, the doubt is, ma'am, don't open previous one, ma'am. I tell my doubt. Ma'am, we left, why, ma'am, we left linear regression due to probability lying between 0 and 1.
Yes, basically, the linear regression gives you an infinite constant continuous number, right? And you say from those 3 or 4 numbers we take the maximum. This is what you were doing, right? Yes.
Yes, ma'am. Ma'am,
Yes.
suppose anyone ask why we left linear regression and why we use logistic regression, then how we can answer?
because because the maximum thing is not completely
Forward
you
in
know
linear regression.
is good for estimating the class values. Okay, let's say for example, uh, let's say there is a dog and there is a cat. Okay, so there is a particular human being. I let him see the
Yes,
cat
ma'am.
and
This thing is, ma'am, I understand, ma'am. I want to say that, ma'am, probability is also become the reason of the left the linear
yes.
regression.
Yes, because we choose the maximum probable output. But linear regression has no constraint that is satisfied for probability. That's why we come to this probabilistic definition.
So
Now we
probability
have
is also reason for left the linear regression. Linear.
yes.
Okay, ma'am. Got
Okay.
it, ma'am. Got it. Thank
Okay, so sigmoid function, what you have asked, this px is sigmoid. Yes, true. This is called sigmoid function. And now, because these betas, we don't know the value of beta. I am just throwing you that this beta you have calculated using linear regression. But here, because this is another type of regression that is logistic with probabilistic outputs, so we will be using some more definitions, some more things to associate how to calculate good beta. Okay, ma'am, how log this problem can be solved? Just think of it na. Look, I can't. This was the thing na. 1 minus px is equal to, let's say, beta x. So log, when you take it here, it is like e of beta x, px 1 minus px. Just solve it. Simple. It's a simple thing. You can solve it. All right. So I was talking about maximum likelihood. So
What was
basically,
just this example which you wrote? Can you please explain why you what was that when just e raised to beta x? What was that example?
that's what, ma'am, same thing which you told me na. It's someone asked me ki how to solve that, the last equation, e to the power, same thing na, which when you
But there was beta 0 plus beta 1 x. So how? Oh, you made it all together. Okay. Fine. Got it. Got it.
okay. So basically, last time what we have done, we have seen that okay, I need help on computing the likelihood observing a data set given the model parameters say 0, 0, ground to 3, 0. Look, I have some questions here also. Just move, let's move. Okay, so basically what I wanted to calculate the probability. I have the function of probabilities, but I want to calculate beta also. So these betas are not calculated easily. These betas is to be calculated with some manner, with some which you like. In the last time we use mean square error, right? In the regression problem we use mean square error and we minimize it, we use differentiation.
Yes, ma'am.
Here also we can't use mean square error, we use maximum likelihood estimation. Why? Because probability is to be maximized, error is to be minimized. There we talk about error, here we don't talk about error. Here we talk about likelihood estimation. Likelihood means how much probable the x will belong to class 1, how much possibility means you can see that
Is there
the
an
probability is
equation
to be
for this?
maximized.
Is
Okay,
there
so
an equation for this like formula for likelihood?
sorry.
Is there any formula for this likelihood?
Yes, just think about it. You want to estimate the probability of x, right? This x is to be maximized. Now we have two classes, either 0 or 1. So that's why it is written as, let's say, just think about it. Let's say just look at here. These are the two terms. Look, see carefully. Don't see now this product of I to n. Just leave it. Just think about the inside term. It is written as p of xi to the power gi. Okay? Then 1 minus p of xi to the power 1 minus gi. Why it is written as? Let's say the probability, there are four possibilities you can have. Okay? So I am going to give you those four possibilities. G is your ground truth. P of X, I would say, is your estimated. So let's say G is 1 and you got 0, or G is 1, you got 1. The other case will be G will be 0, you got 1, G will be 0, you got 0. Okay. So what is the probability that the Px is 0? That's why it is written as P of X G plus 1 minus P of X 1 minus G. So where there is 1 minus G, it means the G is 0. Where there is completely G means if the G is 1, then this term will be activated. If, okay, because 1 minus 1 will be 0. It will be 0.
Yes,
Just
ma'am.
think about it, right? If G will be 0, then this term will be neglected, because this is okay. So this term is P of X is 0 is nothing. Okay, all right. So basically that's why we choose this type of function, so that if your ground truth is 1, then one term can be activated. If the ground truth is 0, the other term can be activated. So this is how this 1 minus Px is the probability of failure with 1 minus d. It means it should be 1 minus d. Px is the probability of success and it should equal to g. That's why we use this type of function. So we take the addition of both of them. Just see it here. So okay, so p of xi gi, let's say the ground truth is whatever the value of probability, ultimately the ground truth is 1. So if ground truth is 1, the 1, yes.
But in this slide, pxi to the power gi, there is no plus sign. It's
Oh,
represented
sorry. Oh,
multiplication.
sorry. It's not plus sign. Plus will be after taking the log. It means we are calculating whether the value will be 1 or 0. Let's say, just think about it. Um, mm, uh, Ground truth value is 1. Okay. So ground truth value is 1. The first term will be activated. The second term will be 1. Simple. Okay. Just think about it. There are two terms, p of xi to the power gi, 1 minus p of xi to the power 1 minus gi. There are two terms. Okay? If the ground truth is 1, just think about it, the second term will be 1. It means it will be neglected. No value will be coming out of there.
Okay, ma'am.
All right.
Ma'am,
If
ma'am, in previous time, there the sign of plus is no needed, ma'am. Here there is no plus, ma'am.
sorry, I have written it
Okay,
by
okay,
mistake.
okay, okay,
Okay.
ma'am. Yes, ma'am. Okay, yes.
Okay. Second thing, what you have asked, someone has asked like p of I. P of xi is the probability of this x. Okay. All right. One thing is, you can see here there is a sign of this 1 to n. This is not summation, this is called product. So it means that 1 to n means, let's say there are n number of samples. So the first sample, the probability of first sample into the probability of second sample into the probability of third sample into, means what I wanted to calculate the probability of whole data. Okay. Let me ask you this simple probabilistic approach. Let's say there are 3 students and I want to calculate the probability that the students will go for lunch outside. Okay. So will you add their probability or multiply their probability?
Add their
So
probability.
you will add when I'll say either one of them. You add the probability when their question is of or. I'm asking if all four of them, I should have asked the question that what is the probability that all of them will go for the lunch outside?
Add them, ma'am. All of
No,
them.
you have to take product, multiply. If I am talking about all, It means, let's say I want to take out the vote that all of you, the students, there are 50 students joined here, all 50 students are able to understand. It means the probability of first student into second student into third student. If I am adding them, means I am giving a chance of or. It can or cannot. Adding
Okay.
is not right. So this product is associated for different data also here. So it means the probability of first input into the probability of second input multiply the third, fourth and n. That's why it is written as a product of 1 to n. Is that clear how this equation comes?
Ma'am, that happens in both the cases of independent events as well as dependent events, because the probability in case of independent events is calculated differently than in case of dependent events.
The observation, actually we assume when we talk about this that all the individual events are independent. That's why we are
Oh,
taking product. Okay.
okay.
All right. So this is to be maximized. So for this to be maximized, obviously we have to take the derivative, but derivative of products is very basically typical to do. Ma'am, oh, I got the answer. Px is equal to 1 more. Okay, thank you. So basically, to remove this product, we take log of both sides, because product, taking log of product converted into summation. All right. So I am taking the product, sorry, logarithmic both side. So taking the log both side, this product is converted into summations. Is that clear? So just take the
But
log
what is the
inside.
need for to convert it into summation?
Because I have to take the derivative, right? Because when we are going to maximize or minimize any equation, we have to take the derivative with respect to the variable and put it to 0. Okay, so taking the derivative, the first equation, the written here with the product, just consider the derivative of products for n products, how you can calculate it. So it's a very typical task. So we convert it into log so that our product can be transformed into summations, and the taking derivative will be easy.
Yes.
Okay, so this is now the function. So someone has given me that model parameters are given to you 0.8 and 0.5, ground truth is 1 and 0. So this is your final equation. The ground truth is 1, right? If the ground truth is 1 and your parameter is given to you, okay, so this ground truth is 1 and your probability of x is given to you, you can calculate this equation easily. So this is your first one of the question that is given in this assignment here in the PPT also. Okay. So basically this is your log likelihood. So you can simply use this, and you can use the derivation of it to calculate the beta. So I'm not going into deeper details, but I'll just upload some handwritten notes, okay, in which this gradient descent Newton-Raphson is calculated. So I'm just giving you that. If there is any issue, you can ask me later, because it's not easy to solve the derivation. We use some Newton-Raphson method. Newton-Raphson method, just look it out. It's a method in which at each step you optimize your output. So those steps are calculated. So how they are calculated, I'll be uploading it there. If you have any doubt, you can ask me also. Okay. So
Ma'am,
this
give
is
this ma'am slide link also, ma'am. Slide link. This slide link.
slides will be already will be present there in your
Okay.
problem solving model. Yes,
Okay.
it is already there. Okay. So basically, this was your logistic regression. So now next is your linear discriminant analysis. So first part was linear regression. Second part is your logistic regression. Third part is linear discriminant analysis. And I want to solve one question related to it. So I am giving you the whole thing is present in this PPT, and I will be having about half an hour. So first, let me discuss about what is linear discriminant analysis. Secondly, how to calculate it. Then we can go into deeper mathematical details. I have some maximum likelihood function for this also. I have solved it. Similar concept is there as we have seen in logistic regression, but now some changes are there which I will tell you how. and we'll see some questions related to it so that you are able to solve some questions also. Okay, so basically, as you have learned PCR, principal component regression and partial least square method, in which we select some features. Okay, here also linear discriminant analysis is a way where you can select some features. In PCA, what you have done, you maximize the variance between the attributes, right? Where the axis is which axis the maximum variance is there, you choose that. Here I am using that variance thing itself, but what I am doing is the data is belonging to different classes. So what I wanted, the difference between classes should be more.
Excuse me, ma'am.
Yes.
In LDA, we have to maximize the separation between the different classes. Am I right?
Yes, that's what I'm saying. You have to maximize the difference between classes as well as minimize the difference within classes. There are two terms, between classes and within classes. For example, let me give you one example. Let's say there are some 3 or 4 classes. 3 classes are there, red, blue and yellow. Okay, so what I wanted, these 3 classes should be separate enough, so long distance from each of them. So between class difference should be more. But what I wanted, yes, I'm repeating the statement. What I wanted, the 3 classes should be separated as far as much, right? So that I can easily classify data. As well as I wanted the data within each class, means the data within one class should be close enough to form a cluster. So what I want to say, in PCA we only think about variation between attributes. Here the variation between classes should be maximum, as well as within classes the variance should be minimum. So there are 2 types of variance we are going to handle here. First is between classes. This means the red, blue and yellow, between these 3. Okay, so obviously is between these I want to maximize, but the 4 points in blue class should be close enough so that they can be classified easily. Getting my point? So I have given you 2 statements. First, maximize between class variance. Second, minimize within class variance. So there are 2 terms, within class and between class. Is that clear? This is the major role, major objective of linear discriminant analysis. Okay, all right. Question is how to get this between class and basically between class and within class. Okay, so Abir, this is recorded class. The recording will be given to you in your portal, the NPTEL portal. Okay, so I am going towards, okay, all right. So basically this will be coming under theoretical concept. So here this linear discriminant analysis is not for just binary classes, it is for multiple classes. So in logistic regression, what I wanted, y, probability of y is equal to 1 given x. What is the probability if I give you x that it belongs to y? 1, right? Here I am saying it is not just for 1 and 0. So any class, let's say if I give you a picture of a dog, what is the probability it belongs to dog? What is the probability it belongs to cat? What is the probability it belongs to human? What is the probability it belongs to some other species, right? So there are multiple classes, first thing. So this is the major difference between logistic and this LDA. Now same thing, maximum likelihood. Oh, it's a very good approach, we have to formulate it. But just let me know one thing, in maximum likelihood approach we use what terms we have used? We used probability terms, right? What I tell you, in maximum likelihood I wanted to calculate the probability of x1 into probability of x2 into probability of x3 into probability of x4. There the classes are only 2, that's why it's more or less like okay, the probability whether the x1 will belong to 1 or not, x2 will belong to 1 or not. So now there are multiple classes. So for that, first thing, I want to create a maximum likelihood function. Second thing, in logistic regression, we have sigmoid function, right? Here I don't have any function. So when you don't have any function, you choose Gaussian as your function. So first thing is कि you will use Gaussian as your probabilistic function. उससे पहले यहाँ अभी किसी ने बोला था मुझे कि there is some rule called Bayesian rule. Okay, so to calculate this p y equal to k given x, we use Bayes rule. So Bayes rule is given here. You know what are the probabilistic approaches in the zero tutorial, zero lecture, zero week. You have those terms. So I'm not going deeper into it. Basically, Bayes rule is more like, it is written as p of y given x is written as p of x given y, probability of y above probability of x. Okay, so this term is also called as total probability term, and we have to take the maximum out of it. So when you are taking the maximum, or so it means, and it is same for all the x, so that's why we can remove them. So we can just say this is proportional to the above numerator. So when we want to calculate this term, we just use these two terms. So this is called likelihood, and this is called prior probability.
Ma'am, can we use this Bayes theorem in our linear regression also?
You can use that, it's not a big issue, but
Okay.
because it's not a big issue. Actually, major thing is like this. So if you will somehow calculate it, because the output is in the form of 1 and 0, that's why we formulate it in more like a binomial form.
Ma'am, how do we use it in linear regression, the Bayes rule?
Not linear regression, in logistic regression. Because you are using the concept of probability, na? So you are going to use in classification, not in regression.
Okay.
So there we have used some binomial type of function for calculation of the likelihood, because the prior probabilities are included
So
there.
instead of the px by 1 minus px, we should use this one. No?
You can use that. It's just a formulation.
So we should take log of this again.
Yes, we will be taking log of this again. So it's more like, there you have used like you have used this function p of x. You used p of p to the power g 1 minus p to the power 1 minus g. You actually use this thing. Okay, here I am telling you this is the actual formula of likelihood. So because you have only two classes, ground truth is only in between 1 and 0. That's why you have chosen to be simple. But if you are going to use this, you can maybe coming towards this convergence also. So you can try it. Okay. So basically, I wanted this. In logistic regression, I denoted like this. In this LDA, I am taking a more generalized approach, and I'll be using this one. So basically, this again is calculated for all x. That's why there is a product here. So P of x given y and P of y. So P of y can be easily calculated. So let's say there are, in the previous example, we have 9 rows, 3 classes. So you can have the prior probability from how many samples belong to class 1. What is the probability? Okay. So prior is more like, in the same example which I have solved for you, we have 9 rows. So there are 9 samples in which 3 classes are there. Okay. So let's say class 1 has 3 samples. Class 2 has 3 samples. Class 3 has 3 samples. So it means 3 by 9. This is the prior. 3 by 9. This is the prior. Let's say, I am giving you another example. There are 10 classes, 10 samples. Okay. And this class 4 has 4 samples. So it will be 4 by 10. 3 by 10. 3 by 10. So this is the prior. It means what is the probability your classes are there present in your training data. So how many
Numbers
samples?
of classes by total numbers of column.
Yes. This is what the probability is, right? So that's why it is
Yes,
called
ma'am.
prior, because you know it priorly. Okay. So this can be
So
calculated
the
easily.
prior and probability is same here.
This is prior probability. Probability is a
Okay.
major term, but this is how you can simply calculate it. Now,
Okay.
now question is about this. How to calculate this? In that, the logistic regression, Px is given by sigmoid function. Okay. Here, we will not assume it at sigmoid. We will assume it as normal function. Normal means Gaussian function. So wherever you got stuck, we assume that the data is from the Gaussian parameters. That's why we have some mean variance associated with those distributions. So we take this Px by y as Gaussian distribution. So Gaussian is written here. So I am just this one. This is your Gaussian function. Okay. So here the sigma is covariance matrix. X is your multivariate variable. Mu k is your mean of each class. Okay, so these are the parameters of this function. So this function, I am assuming it. So one thing, I am now going towards LDA. Same thing is given to you. Now, same maximum likelihood function will be applied for this function. Major difference between LDA and QDA is this covariance matrix. For LDA, covariance matrix is same. So it is not variable, but QDA, it will be variable. So now I am not talking about QDA here. I'll be talking about only LDA. So basically what we will see here, in linear discriminant analysis, we use this function in which this sigma is same. It is not with K. For each class I am not calculating it. It is same for all classes. Mean you can calculate. So let's say there are 3 classes, red, green, blue. Take the mean of blue samples only. Take the mean of red samples only. That's why it is written as mu k. Okay. So assumption is also written here. Covariance is 1, means all. If I give you an intuition here, in LDA, where the LDA can be helpful, where the Gaussians or the clusters are of same size somehow. Okay, so let me just give you a visualization over this. Let's say this is your data. So this and this is nearly same. There you can apply LDA. If the data is like here, like this, you can't apply LDA. You have to go for quadratic discriminant analysis, which we will not be going to discuss here. Okay. So many terms are going to be thrown in the PPT.
Ma'am, not clear, ma'am. Unable to understand how this first figure
Look,
is same, second figure is different.
the size are different. Here these are same. The variance is same. I am saying this variance is same. If you have to pick this up and put it somewhere else, then this should not be changed. So it means if these ellipses are of same size, nearly same size, then LDA is applicable, otherwise not.
Oh, nearly same size. This is the
Nearly
condition.
same size. We can't say, it's more like a hard restriction that we can't say like that. Okay,
Oh,
it
yeah.
should be equal. It should not be completely equal. It never be. Okay, in the
Okay.
real world, we will not get equalities, right? So somehow we wanted nearly equal. If nearly equal, LDA will be useful, otherwise not. And how to solve this likelihood function, I'll again upload some handwritten notes there. Okay, so because first I wanted to tell you some questions related to this. So let me come towards the question. So these are things that you can simply go with it. Okay, so I'm just going to coming towards your question. You can simply go with this because I don't have much time for this. All right. So I told you two terms, between class and within class. First, we will calculate between class variance. So how to calculate? The goal is to maximize this between class variance. Just think of it. There is another term you will see here, projection. Okay. So you will be sitting in your room. Okay. And let's say there are some, can you see your shadow on your floor? Yes or no?
Yes, ma'am.
Yes, this is
Yes,
a
ma'am.
very common example of projection. So you are in a 2D or 3D. I can't say 3D because you are stick to the ground. So I can say that you are in a 2D, sorry, 3D, yes, sorry. You are in a 3D environment, your body, and your projection or your shadow is on the 2D floor. Okay, so this is called projecting data. Am I clear? Have you now? Can you just imagine the projection? What I am saying. So it's a very simple thing that from 3D to 2D, what you draw on your paper is called projection. Okay, so when you draw the top view, some of a building, of a machine, it's called projection of that thing on the paper because it's a 3D. All right. Similarly, what we wanted between classes, I want to maximize the variance. So what I want actually geometrically, I can say, let's say there are some classes. This is class 1, this is class 2, and this is maybe class 3. Okay. I want to maximize their variance. It means I wanted them to be far apart so that I can easily distinguish them. This is what I wanted. So what I want, their mean, because how can I represent such a huge amount of data? The common parameter, I can use mean, average. So what I want, their mean is to be projected in some space so that it should be maximized. So we will be having, this is a simple 2D data which you are seeing here. Just imagine some objects are floating in air. Okay, so what I want to project them in some space so that they can be very far apart, either higher dimension or lower dimension. I'm not talking about that. So my main aim is to make them far apart. So increase the variance between the classes. So for that, what I am going to use, I am taking some notions. So here, let's say there are two classes. So M1 and M2 or mu1 or mu2, any notion you got it, these are the mean of the classes. So how you get the mean? Simply you have the samples, take the average. Okay, I'll be giving you one example also. Next is projection vector, because I'm saying to project the mean in some space so that we can increase the variance. So your shadow is projected on the floor. Okay, mathematically, let's say your body is represented with a matrix. Okay, your shadow is also represented with a matrix. So you have to transform matrix 1 to matrix 2 using some operator. So that operator is W here. Okay, and we don't know what is W. Ultimately, we want some good W so that the variance can be high. The variance can, between class, the distance can be high. Okay, so this is the major parameter that I want to calculate. This is the objective of LDA. How to calculate it? We'll see. So W transpose X is the projection. That's why I am saying you, this X is your matrix 1. This W transpose is your operator. And after what you get, that is the projection. So it's your shadow. This X is your body. This W transpose is the operator. And when you apply this operator on your body, you will get your shadow. The output will be your shadow. So this can be seen like this. Okay. So how to calculate it? So simply what I will do, I will take the projection of mean 1 because I have two classes. I will take projection of mean 2 and I take the difference. Obviously, I want to maximize the difference, right? So I take the difference and I want to maximize it. So to maximize it, what we want to do? We just want to use differentiation. But अब question ये आता है, is this the only condition? No. I have another thing also. So ultimately, this can be simplified as W transpose can be taken it out as the same common variable and M1 minus M2. Now what they say is this W, this W is not much of my importance. What if this W is 1, only 1? Okay. So what I wanted, I want, because I am taking the norm, right? This norm is the square. Okay, so this norm means I'm taking the square, and if by some way I can normalize this W, normalize means I just take the value of W, the norm of W is equal to 1, then my equation will get simplified. So what I'm going to do, they say that we took such projection such that the norm of W is equal to 1, so that we can work on M1 minus M2. Because let's say if the W value is so much high, then it will obviously affect our data, as we have seen in linear regression also, where we want to restrict, like in logistic also, we want to restrict our data to 0 to 1. So this restriction, like in ridge regression, I told you, because the values are too much high and I want the weights to be lying in some low range, so that's why I wanted W to be lying normalized to 1, so that my this scaling of mean of different classes should not be unbounded. Okay, so ultimately what I need, I take the mean of all the classes. You can easily calculate that. So how to calculate this within class variance? This was between class. So for between class, what you want to do, M1 minus M2 square, that's it. Because M1 and M2 is vector form, so you have to take M1 minus M2 transpose M1 minus M2. Means x square can be written as x transpose x. That's why I'll be using that thing also. Okay. So second thing is, first thing is between class, second is within class. You know the formula of variance. How to calculate variance? Can anybody tell me? Can anyone let me know how to calculate variance?
Then mean minus sigma.
Mean minus sigma nahi, x minus mean.
It's a summation of squares of the difference between the mean and the data points average, madam.
Good. So here also it is written like this, x minus m1, and you say square na, because these are vectors. That's why we take matrix multiplication of x minus mean 1 into x minus mean 1 transpose, because we can write, look, in vector form. I just giving you this note. If you want to calculate x square, so either you have to write x transpose x or x transpose. This will give you two different matrix. Now here I am talking about this, okay, because my projection is in this form, and this is your dot product. Actually, x transpose x is your dot product, and this is your cross product. So this x square term, either you use dot product or you use cross product. Here I am using cross products. That's why it is written as x transpose. So it's a simple thing to calculate the within class variance for class 1, x minus m1, x minus m1 transpose. Same for class 2. So the total will be the sum of these S1 and S2. So similarly the S1 and S2. I am jumping now towards a equation that is called Fisher criteria. So this is the Fisher criteria which say that I want to maximize the between class variance and minimize the within class variance. So SB is your between class, SW is your within class. Here WT transpose W is written for projection because you are using projections of them. That's why they are written here. So when you get this and you want to calculate the best W, you just derivate it with respect to W and equate it to 0. So when you do that, I am not going into deeper details here. I will be giving you those notes. You can see I have solved it. So basically, after taking the derivative of JW with respect to W and equating it to 0, you will be having this type of equation. So this type of equation is more like eigenvalue, eigenvector. So here I just have to calculate the eigenvector of maximum eigenvalue. So when you get the eigenvalues, you just calculate it, and from the largest eigenvalue, like in PCA you have done, just calculate the eigenvector. This is your W, and this will give you the direction. So I am giving you one question to solve this. Okay, so let me just look. This is your data. So after getting this question, maybe many things will be get clear to you. This is your data of some classes C1 and C2. I have to calculate two things, between class and within class. First, I am calculating between class. So for that, I need M1 and M2. So this is your class 1 data, this is your class 2 data. I'll take just average. So x1 ka average 2 plus 3 plus 4 divided by 3. 3 plus 3 plus 2 divided by 3. Similarly here 7 plus 8 plus 9 divided by 8. 8 plus 7 plus 9 divided by 8. Okay. So is this clear, this mean calculation? यहाँ तक किसी को कोई problem है? Mean.
No, ma'am.
Okay, now this is your M1 M2. We calculate between class using this. So how to calculate between class? Between class is M2 minus M1, M2 minus M1 transpose. So M2 minus M1, this 8 minus 3, just see here, this is your 8, ठीक है, 8 8 and 3 2.67. So 8 minus 3, 8 minus 2.67 is your M2 minus M1.
Can you repeat that once more, this last step? How that 8 from where? Which is that 8?
Ma'am, this the last thing, average of the column, 7 plus 8 plus 9 divided by 3.
No, you subtracted 8, no, something. Okay, 8 minus.
Okay. So after this step, you calculate two things, between class and within class. So between class means M2 minus M1. So just calculate M2 minus M1. 8 minus 3, 8 minus 2.67. Just see here. 8 minus 3, 8 minus 2.67. So this is your M2 minus M1. Okay. Now take the transpose. So it will be 5, 5.33. Is that clear?
Yes.
Okay.
And can you show the previous slide?
Okay. This one?
Yes, ma'am, got it.
Okay. So these two matrices are there and their product will be between class. So I take the product. This is your between class variance. This is SB. That's it. Simple. It's a very simple thing. Okay.
Madam, how you got this 5.33?
Sir, M2 minus M1 is clear. 8 minus 3, 8 minus 2.67.
Okay, madam, thank you.
Okay. So this is your between class. Now we will skip to, we will go towards within class. For within class, what I have to do, this is your actually the formula, xi minus mu k. So we will doing it for each class. So let's say we start from class 1. This is your class 1 data. X minus mu 1, x2 minus mu 1. Okay. So 2, 3, 4 was your x value. 3, 3, 2 is your x2 value for class 1. And you have the mean also, 3 and 2.67. So what you will do, 2 minus 3, 3 means just separate, subtract 3 from x1 and 2.67 from x2. Is that clear? Is that clear? This x minus mu 1.
Ma'am, how do you got transpose term in previous slide?
Sorry?
How do you calculate transpose term in the previous slide?
Transpose
the second term. M2 minus M1 transpose.
This one, na? Transpose means you have in a column 5 and 5.3. Just interchange row and column. Transpose means interchange row and column. What is in the column?
And how we will get to 25 and 26.65, madam?
Sorry, ma'am?
Sir, how we will get, madam, 25 and 26.65 values, madam?
Ma'am, this is the matrix multiplication. This M2 minus M1 matrix is 2 cross 1 and M2 minus M1 transpose matrix is 1 cross 2. 2 cross 1 into 1 cross 2 will be giving 2 cross 2. Matrix multiplication.
Okay, madam. Thank you.
Okay.
Thank you, madam.
Okay. So this is your x minus mu 1. Okay. Now what I wanted, this is your x1 minus mu 1. Look, I have given you this minus thing here. I will be writing it as separately because I have to take the square of it. Square yani cross product. So I will take, this is your x minus mu 1 and taking the transpose is like this. Is that clear? This is the same thing, x1 minus mu 1 and its transpose.
Yes, ma'am, got it.
Ma'am, can you show the new one table, ma'am?
New one, the previous one?
Yes.
Ma'am, mu values.
Mu values are the same, na? This one, 3, 2.67, 8 and 8.
Ma'am, these are the new values?
These are the mu values. Mu means mean. M1 is also mean, mu1 is also mean, whichever terminology you are taking. Okay.
Yes, ma'am. Yes, ma'am.
Okay. So this is your X transpose and this. So when you calculate its product, you will get this matrix 2 cross 2. Okay. This is your product. Similarly, we will do it for next class. So this is for class 2 data. Similarly, we will calculate X minus mu, its transpose, and we will get a same matrix here also. So the within class variances, the addition of these S1 and S2. So above is S1, below is S2, just get the sum of it. So we will get this sum. So now you have two matrix, SW, this green one, and in the previous slide there was SB. Okay, you have calculated that SB using M2 minus M1. Okay, is that clear? These two matrices you have to calculate. Is that clear? Any doubts till now? We are just
Madam,
yes, yes.
this SB, SM calculate regarding SM, we have taken x1 minus mu and multiplied by x1 minus mu transpose. So is it as vector related multiplication? In the earlier discussion you explained about it. There are two things, dot product and cross product.
This
So
is actually simply matrix multiplication. X1
simply
minus mu,
okay.
simple X multiplication, because these are written as the multiplication of X and X transpose. It is, that's why it is called cross product or dot products.
Okay.
The squares can be in the form of X transpose X or XX transpose. So these are called cross products or dot products.
So in this case, we use it as X transpose.
Yes, XX transpose. We are using it.
Okay. Okay, ma'am. Thank you.
So, ma'am, it is dot product or cross product?
It is cross product. X transpose X is cross dot product. पहले transpose लगता है, then it is dot. Okay. Now this is SW. We have SB. We have to move towards Fisher criteria. So Fisher criteria say that your JW. Okay, JW is, you just have to calculate two things here. You have to solve this equation. For fully getting the value of W, you have to solve this equation. The SW inverse into SB. So you have to calculate the eigenvalue of SW inverse into SB. You have SW, get it inverse. You have SB, get the product. So what you will do, from SW calculate inverse of it. You have SB, then calculate the multiplication of last two matrix, which you will get this. So now this matrix will be used to calculate its eigenvalue and eigenvector. So the largest eigenvalue, associated eigenvector, will be the value of W. It's like that. So now this is a simple matrix. Apply eigenvalue mechanism here. A minus lambda I is equal to 0, determinant of it. Solve it. You will get, I have solved it actually, and it's in the paper, like, okay, I'll upload it also. So basically when you will solve it, there will be two values, 16.75 and 0.01. So 16.75 is the largest value. So solve for the eigenvector for 16.75. The vector you will get is the answer for W. Okay, so there are two things in this question. First thing is JW criteria. JW criteria is between, over, within. So calculate SB, calculate SW, and take the ratio. This is your JW. Okay, and if you want to solve for W, just calculate SW inverse SB. This is the same thing. Okay, SW inverse means, look, what I tell you, JW is SB SW. Okay, if I want to write it as matrix, I can write it as inverse, right? SW inverse SB. So this is the same thing. So this is very important thing. So either you can have a question with calculate JW with these values, or the question कि solve for W. So this matrix is used for eigenvalue. So let's say this matrix is A. Okay, solve for A minus lambda I, calculate lambda. Using the lambda value, calculate W. So this W is used for
Ma'am, could you
your.
just repeat what the two types of questions are? One is for solving for the eigenvalue, the other one?
The other one, simply a question can be asked that what is the criteria, this DW criteria, okay, this Fisher criteria. So this Fisher criteria is SB over SW. Let me take you to the question, okay. There is one question at the end. There are questions and their solutions there. In some way I have given you some hints to solve them also. So basically, look, this question. So within class variance is given to you, neta 1 and neta 2. Okay, so SW is, look, this one. So within class variance is given to you, this 1 and 4. So total SW will be 1 plus 4. And your projected means are given to you. So projected means, if it is given to you, M2 minus M1 and M2 is given to you. So M2 minus M1 ka square, right? Transpose we are taking because it was in vector. These are the simple terms, so we don't need to take the transpose, we just take the square. So JW is between over within. So between means 1 minus 3 square, this mu1 minus mu2, okay. And within means S1 plus S2, so sigma 1 plus sigma 2. So it's simply 0.8. This is the first type of questions. And another type of questions can be simply, you have mu1, mu2 and just calculate the vector W. So here the SW is identity matrix. You can't, you don't have to go for those inverse calculation and all. So these are the two questions. Some hints are given here also, okay. So these are the basic three things that in this week we have covered. Linear classification with three methods. First is linear regression, second is logistic regression, third is this LDA. So in LDA there are two important things, between class and within class. With the help of these two attributes, we solve for Fisher criteria to calculate the direction of W. Okay. For logistic regression, most probably major questions are more like basically, let's say you have given a ground truth, your probability is given to you, or some beta values are given to you to calculate the probability. These small questions are there for assignments. And for linear regression, you all know, okay, just calculate the linear regression for all classes, take the maximum value and find the output. So these are the three important topics for this week. Now you can ask questions.
Ma'am, what is the relation between this Fisher information and posterior probabilities of classes? Because actually we are having one question related to that, but I could not understand that relation. What is how to approach the problem? I did not understand.
Ma'am, this Fisher is actually based on the thing that you can say about the variances from the means. Okay, so we can say that they are basically posterior is more like the likelihood functions basis. Okay, so likelihood, what you calculate in the likelihood, there are two things, okay, that x over y and that's prior probability. So with the combination of those two, we want to calculate the posterior. What you want to ask, I didn't get it actually, because these two things are somehow in different ways.
Now here we are trying to use the Fisher information to calculate the likelihood.
You can say that we are projecting the data in some form so that they can be discriminated far away.
Actually, here anyway, are we using something like the base rule for this LDA?
Ma'am, base rule for LDA, actually, yes, there is a method that we use it. For example, okay, let me tell you this. This mu information, right, is important. This variance information is important, and the basis of Fisher is based on this mean and variances. So how do you get this mean and variances? So this mean and variances are calculated using likelihood functions. So basically the likelihood is in which the probability of all the data points include, right? And I told you we assume that the probability function of LDA is Gaussian, in which two things are there, mu and sigma. Can you connect these 2 points? Fisher has two things, mean and sigma, means mean and variance, and likelihood, where we have used Gaussian, has two parameters, mean and Gaussian, mean and covariance matrix. Connected?
Okay.
It, the Fisher is using mean and variances. How the mean and variance is calculated, you know by statistical terms. Okay?
You have shown how to find out that Fisher J also. But now what do you do with the J? How do we use it for classifying?
Ma'am, it's basically, it's more like this W is a direction. So this is a discriminant boundary you will get.
So using J, you will be finding out that lines.
Yes,
Okay.
those hyperplanes we are finding it out, but you are using the information of mean and variance. Okay.
Okay.
You are using what formula you have used for mean? Take the average, correct?
Yeah.
So if I throw you something, can you means maybe you don't remember the correct formulas, but is the formulation of mean of exponential distribution is same as the Gaussian distribution? Yes or no?
I did not understand that question. Is the formulation of the mean of the Gaussian distribution same as?
Exponential distribution or Poisson distribution, there are different types.
No.
There are different.
Oh,
It's
but
not
mean will
same.
be same. Huh? Oh.
Huh?
But mean will be same for everything.
Yes, ultimately the mean you know is because you know the concept of mean. It's more like an average information, right? But the formulation is not same. Formulation is not same. So ultimately we are getting this mean and variance values, the actual mean, that how the mean is to be updated is from the likelihood function. So let me just take you there. Maybe in some slide I have put it down, or actually I have solved it on paper. So most probably it is, this is your Fisher. Actually this Fisher criteria hai na, is and another way to see the linear discriminant analysis. But what linear discriminant analysis is same as those MLPs, this likelihood function. So this is your function and this is your log likelihood. Basically, no, it's not. Just see this function, okay? So this is the function in which two terms are there, mu k and sigma. So this mu and sigma are the parameters now. In the previous one we solved for beta, okay? Here when we put this f, this is more like a px, okay? So this px, if we replace, like in place of sigmoid we place it there, and in sigmoid we have the parameters beta. In this function we don't have beta, we have mu and sigma. So the equation to update mu and sigma is same as we have calculated in statistical measure. So it is proven from this likelihood formula that after getting the derivation from this, the mean is ultimately updated with the same formula as the sample mean.
Okay. That's fine. Now what is D here in the same equation? 2 pi raised to d by 2.
Actually, ma'am, this G is for dimension.
Okay.
X is multivariate. So,
Okay.
but here it's more like a constant, because we generally have constant number of dimensions. We don't use it because in differentiation it will obviously be zero.
Thanks. Okay.
Okay, so this is what the three methods. I basically upload it. And yes, obviously, I need your
Ma'am,
suggestion and feedbacks for this, because it's for me it's more like more mathematical and I am not I can't get it that if it is clear to you or not. Many mathematical concepts I can't cover it here
And one
because
doubt
it takes.
actually, when do we use LDA? Which is better? In which situation we will choose LDA, and which situation we should use logistic regression?
Ma'am, same things like the Fisher criterion. Basically, it's kind of categorize things. You can do in multiple way, like regression or KNN or another way. So when to use what? So what is the, say for example, I have large number of data. So which method I should use in that case? If I have less number of data, what methods I should use?
Sir, actually, thing is, the less number of data will not work for machine learning anyway, because either the bias or variance will, obviously, there will be more bias and your model will be underfitted. So you have at least some amount of data, good amount of data, so that you can say that your model is good enough. Okay. Secondly, these algorithms are developed in stages. Okay. So first we use the linear regression. There are some, questions regarding this. So basically, the probabilistic concept is tackled with logistic regression. But still, logistic regression is a variant of linear regression. It is not very powerful for multiple classes. All right. So when the boundaries are more complex, we can't use that. Secondly, this linear discriminant analysis is just a way to see the problem with the help of, you can say, the mean and variances, plus using the concept which is very generalized. So we
That
have not
LDA is
assumed
more
anything.
powerful than logistic regression.
Yes, you can say that. Plus, it's a benefit that this LDA can be used for feature selection also. Okay, so
Because of W
because you are
only we are
projecting,
able to, because of W only we are able to reduce the dimension. W is
yes, that's why I'm saying it is more related to projections. All right. Thirdly, but it has its own assumptions. The clusters or the classes should be of nearly same size, same variances. Okay, so if your data is more complex, we can't go for LDO. You have to go for QDA, in fact, quadratic determinant analysis, in which the variances between the classes also changes. That's why here I'm saying that, because I'm taking direct minus, okay, m2 minus m1, I'm not saying one class is more powerful than the other. I'm not taking into consideration,
when
it's
we
not
consider
taking
outliers, logistic is the most powerful. Is it like that?
for outliers.
Yeah, when there are outliers in our data.
uh, Uh, because, ma'am, maybe because LDA will obviously affected by the outliers. So
Okay,
somehow the
okay,
mean
okay.
will be affected. So ultimately,
But
so
ma'am,
So,
you
ma'am, I
one
have the
wait a
question.
minute.
Say, for example, the
Just
boundaries between the categories are clear in one case, and in another case, it's not clear. So, you are dealing with ambiguous data. Which way I should go with either data set?
sorry, get your question. Can you please repeat?
So, I have a data set. It's large enough, but the boundaries between categories are not clear. Or
Okay.
in another way, we are dealing with ambiguous data.
Ambiguous data means you are saying the same data can be classified as one and other classes.
So, for example, I am customer segment analysis. We are doing customer segment analysis, and they are overlapping features. Uh,
Okay. You are actually into multi-model data, or you are talking about Gaussian mixture models, in which what you are saying that let's say some data is overlapped. Okay.
right.
In fact, in the same class also, let's say means you can either consider that as horses, donkeys, and ponies. Okay, so it's a mixture of that. So how will you categorize the pony? Either in
Yes.
horse or in donkey. So basically, sir, this is the major, um, you know, the field of research. That's why, um, if ultimately there are some methods which can deal with these mixtures also. So there are like just think of it. How should I say it? Uh, Basically, you have another way of parameterizing it. So here the function that I have shown you for Gaussians is very simple. But when you go for mixture of Gaussians, you have another probability associated with each mixtures. So now here the complexity is again increased with some more parameters. Okay. Secondly, you also have some non-parametric methods which are into trend right now, in which you don't know how many types, or what you have said na, that ambiguity, how much ambiguity is there in one class. Maybe today you have two types of ambiguities. Let's say after 3 years you get another 3 or 4 types of ambiguities. So it means the ambiguities are increasing day by day, this noise is increasing. So somehow we are modeling it with different types of models as well. So these are very preliminary models. We can't use for those data, means we can use them obviously, but they will not provide you with the good results. Okay. Ultimately, these are mathematics. If you give something to it, it will answer you something. But
All
it is
the
not.
all the three are supervised models, no? LDA, logistic regression, linear regression.
Yes.
All these are supervised models only, no?
Yes. All these are supervised.
Yes.
Classification is supervised.
And which is the model where we use the posterior probabilities to find that discriminant function?
Ma'am, posterior probabilities are that the likelihood into prior is called
So,
posterior
no, you
probability.
suppose we want to know which is the model which is using posteriors to find our discriminant function. Is it logistic regression or is it LDA or both?
LDA. The maximum likelihood function is based on Bayes formula.
But that is what we are using for logistic also, no?
Logistic may actually, that is, you can say, but it's more like a binomial function. I would not say it's more like, because the classes, okay, it's in the form of 0 and 1, it is not considering the prior. It is also using that, obviously. I'm not saying ultimately
No,
the
but
goal
actually,
is.
in today's session, you also said that we can use, if we want the base formula in place of that p raised to g, p of x raised to g into 1 minus p raised to 1 minus t, that one equation you wrote, no? You said there,
That
instead of that p of x by 1 minus p of x, we can use,
Okay.
you mentioned something like that today, that's why.
Actually, ma'am, thing is ki we have to model our probability functions. Okay, so where we have some chance to simplify that, we do that. So in logistic function, we have the chance to simplify because the output is only 1 and 0. But in LDA, we are not considering that. That's why we are using the full posterior formula. Is here also we are calculating ultimately y is equal, what we are calculating, p of y equal to 1 given x. Here the
Ma'am,
p
ma'am,
is written
one
not only
question.
for 1. Yes. Yes,
Ma'am,
go on.
ma'am, tomorrow is the last date of assignment, so you are not solving assignment. So where we can solve assignment?
Sorry.
Ma'am, assignment question is not solving in this session.
Sir, this assignment questions, I have, this PPT will be shared to you. The hints
Because tomorrow is
is,
the last date, ma'am. So
No, actually, the thing is, the assignment questions will not be solved here. We have to submit it and later we'll get the key. I think he's asking for a tomorrow submission.
okay, ma'am. So assignment submission is not daily here.
no assignment. And second thing, this assignment is not, this is the previous assignment. We are not solving this year's assignment. We are giving you the questions that were in the previous years to help you ki these can be the questions, and still in this side, because look, as I already told you in the first lecture, either I can cover this content, or I can cover the assignments,
Okay,
because
okay, okay.
it's,
Achha, one
because
thing,
if
ma'am. Ma'am,
we have to go. Yes. One
your
just one
classes
thing,
will be
Uploading
one
the
thing,
recorded
assignment
and
wait
not
wait wait
questions.
wait
submitted.
wait
You're
So if
uploading the PPT with the assignment questions, no?
yes.
That
So
is enough. I think you're doing the content very well. So it is
Content is
easily
important.
understood.
Yes.
ma'am, let me say one thing. Please give feedback on this link, because I have my device battery is not
Achha,
good enough.
ma'am, last
That's why I have
question,
to
ma'am.
disconnect
Last
from
question,
this
ma'am.
Yes,
device.
ma'am.
Please
Your
give me
regular
feedback.
classes will be held on Tuesday.
Yes, every Tuesday, 6
Thank
to
you.
8.
Ma'am, from where I can watch previous videos because it's my first lecture and I am facing problems in understanding all the concepts.
Actually, you will in your portal where you have assigned, it's a portal of problem solving session. You have to click there. You will have an Excel sheet in which our names are written, videos links are there, and a folder is given to you where the PPT and the content is there. Okay.
Okay, ma'am.
Just one last question. Actually, I still did not understand where the base rule formula will fit into logistic regression. Because logistic regression, two ways we can write. One is as that e raised to 1 by 1 plus e raised to beta x, that equation is there. Whether it is inside that or whether it is inside the other one, that p raised to g into 1 minus p, or whether it is inside that p by 1 minus p, that what is that log it. Where do we put that base?
Ma'am, Bayes rule is applied when conditional probabilities are there. Okay. So conditional probability is I want to calculate the probability P of y equal to 1 given x. This is what I have to evaluate. Just leave it
So
whether
that
it is
part is okay. Now you tell me how
okay.
actually we can put it inside logistic
Okay.
regression equation.
That's what I'm telling you. So basically, don't think about logistic or LDA or anything. We have to calculate P y is equal to 1 given by x. Now this, if this can be modeled using Bayes equation as an LDA where you are taking likelihood and prior, this is the one way. Another way is because logistic regression is not directly using the Bayes rule. Just let me know one thing. If I ask you, if I give you some data and I ask you, just ma'am, please calculate the probability of px given y. Okay, whether you use Bayes rule or you use another rule, the probability should be same. Is that true or not?
Yes, true.
Right. So one LDA is using directly the Bayes rule. The this logistic regression has its own development of its probability.
Okay, got it. Thank you so much. Thanks. Okay.
Okay. Okay. Any more questions? Okay. All right. Thank you so much, guys. Thank you.
Thank you very much. Thank you.
So
Thanks.
let's meet next week, same time. All right. Thank you. Thank you.